What is the smallest unit of information? The smallest unit of information is the information about whether something exists or is absent, whether something's off or on. This fundamental unit of information is the basis for computing because it is robust and also easy to implement. Commonly, we refer to it as a bit. To represent and manipulate these bits, we make use of the electrical components called transistors. These transistors allow us to control the flow of an electrical current by turning them off or on. Whether or not an electrical current flows and whether or not a transistor is on or off, we typically represent with the binary values 1 and 0. And so in a computer we have many of these transistors, and by turning them off and on, we can realize complex operations. Here we have a small example of a logical AND gate that is built using transistors. And in this circuit here we have two types of transistors. One of them, which we can see here, is open when there is no current at its source. And then the other kind of transistor we have here, and this one is closed when there is no input at its source. And closed means that a current is flowing. And so by combining all these transistors together, we get an AND gate. And in an AND gate, the output only lights up if all our inputs are activated. So if B is on, the output is still off or 0. If also A is on, still the same. And then only if all of the inputs are on, so A and B and C are on, our output lights up. And here we can see a more complex circuit that makes use of these AND gates and also some other gates and components to realize a counter. So up here we're counting 0, 1, 2, 3, 4, 5, and then it resets back to 0. In this video, we'll not go deeper into how these transistors make up these complex circuits, but we will focus on the binary system that we use to represent our bits. If we have 8 of these bits, we call it a byte. And we could also say that a byte is a binary number with 8 digits. But now, how does the binary system work? And to answer that, we will first look at the decimal system, which we're all familiar with. Here we have the number 425. The order of the digits 4 to 5 matters, because 4 has the factor 100, 2 has the factor 10, and 5 has the factor 1. So we're thinking 4 times 100 plus 2 times 10 plus 5. And from here we can already tell why we're calling this the decimal system, because each digit, depending on its position, is multiplied by 10 raised to a certain exponent. So for 2 it's 10 to the power of 1, for 4 it's 10 to the power of 2, and for 5 it's 10 to the power of 0. And so we're starting at 0, and then we're increasing by 1 as we go to the left. So if our number were to continue, we would also have 10 to the power of 3, 4, and so on. So with that knowledge, let's go back to our binary system and our binary number. And let's give it a different value to make it more interesting. And now, because we're in the binary system, we multiply our first digit to the right, not with 10 to the power of 0, but with 2 to the power of 0. Which in this case wouldn't make a difference, because something raised to the power of 0 is just 1, but then going one digit to the left, now we're multiplying with 2 raised to the power of 1. And then we again increase the exponent as we go to the left. Now the highest exponent is associated with the digit on the left. And so we call this digit or bit also the most significant bit, because it has the strongest influence on our binary number. Meanwhile, the most right digit or bit has the lowest exponent. And so we call this bit the least significant bit. Now, if we want to convert our binary number to a decimal number, all we have to do is multiply the digits with their respective factor, sum everything up, and then we have our decimal number. And while this is fairly easy to do with a calculator, If we want to do it by hand, we first have to know what 2 to the power of all our exponents is, and after we multiply everything, we also have to perform a lot of additions. And so to make this all simpler, we can use a different method. In this method, we start by writing the binary digits below each other. And even though we changed the formats, we still know that our first digit has to be multiplied with 2 to the power of 7. So we want to multiply by 2 7 times. And then for our next digits, we want to multiply by 2 6 times, then 5 times, and so on. Now, looking at all these 2's, we could say that there's a lot of redundancy. And so the core idea of our method is to carry the result of one line to the next line and only multiply each line by a single 2. And we're also going to shift the 2's down by one line, which does not change the result, but makes the form a little nicer. Now this might sound complicated, but it will become very apparent as we go through the example. So in the first line there's no 2, so we just write 1 equals 1. Then we carry our 1 to the next line, where it's multiplied with 2, and then we add plus 1, so our second digit, which gives us 3. Then we carry the 3 to the next line and multiply again with 2. Then we add our third digit, which in this case is 0, which gives us just 6. The 6 again we carry to the next line, and then so on. To better illustrate why this works, we can look at our first digit and see that as it goes through the lines, it will be multiplied by 2 7 times. And we remember our first digit had the exponent 7, so 2 to the power of 7. And then our second digit, which had the exponent 6, will get multiplied by 2 6 times. And then this continues until our last digit, which will not be multiplied with any 2's. So 2 to the power of 0, or simply 1. Alright, so we can convert binary numbers to decimal numbers. Now, how do we convert decimal numbers to binary numbers? And to explain our method, we'll start with some arbitrary decimal number x. And we know that we can also represent this decimal number as a binary number. So here the binary digits are represented as A, B, C, and D. And we'll already calculate our factors to make it a little bit easier to read. And now our goal will be to find out what the binary digits A, B, C, D actually are. Because if we have them, then we have our binary number. And so to free these digits, what we're going to do is take 2's out of them. So we have A times 8, B times 4, C times 2, and 1D. So out of A, B, and C, we can take 1, 2. So we can also write 2 times A times 4, B times 2, and C. And then our D is separately behind. And so what we can tell from this new line is that our x will be equal to 2 multiplied with something plus our d. And so 2 multiplied with something will always be an even number, so a multiple of 2. And then our plus d will then actually decide if we have an even or an odd number. So this then means if we're starting with an odd number, we can be sure that our d will be equal to 1. And then we repeat this step until we have freed all our digits. But don't worry if this seems too abstract, we'll get to an actual example right away. So let's start with the number 13. And we want to represent 13 as 2 multiplied with something plus d. And to get to this something, we will divide our 13 by 2. And if we are just dividing, this would give us 6.5. And this is not what we want, because our something for the x example was a times 4 plus b times 2 plus c, which is also a binary number. And binary numbers, in our case here, are not point values. So we're going to divide 13 by 2, but using integer division. So we're rounding down to the next smallest number. So in this case, we don't have 6.5, but instead 6. And then we're checking if we're missing something. So 13 divided by 2 equals 6. That cannot be correct. So what we're missing is a remainder of 1. And this 1 will then be our d. So our something that multiplied by 2 plus d equals to 13, that is our 6. So 6 is the a times 4 plus b times 2 plus c, and the 1 is our d. Now, if our 6 is the a times 4 plus b times 2 plus c, which is, as we said, also a binary number, then we can just repeat the same process. So we carry the 6 to the next line, we divide by 2 using integer division, we check the remainder, and so on. So now the 3 that we're getting is equal to the a times 2 plus b, and our remainder 0 is our c. We repeat the same step to also get our b. And then for a, it gets a little bit interesting again, because we just have a 1 left, and 1 divided by 2 with integer division is 0 with a remainder of 1. So 0 indicates that we're done, and the 1 is our a. So that's it for this video, where we talked about bits being the fundamental unit of information and how they're relevant for computing, and we learned how we can convert multiple bits in the form of binary numbers into decimal numbers and vice versa.